So how much fuel would the HLS really need? How many refillings? And a really important question, is Hydrolox better? Now, an outline of today's video is we need to consider what is the real delta V required, what are the ISB of the engines that we're going to use, a very important one, dry mass and payload, and finally, what is the master orbit that the Starships version 2 and version 3 can put in for refilling? So at this point, you might say, why would you even consider using hydrogen? It's got so many downsides. Its boiling point, its density, its low thrust. Let's take each one of them. Yes, the boiling point is low. However, there have been many missions using Hydrolox into space, and there's been a lot of work on extending its use long enough for a moon mission. This includes active and passive cooling systems such as cryocoolers and external louvers. Low density, it does mean that your tanks will have to be bigger. This is a big penalty using stainless steel, but using aluminium, it's not such a penalty, and we'll look at that. Low thrust is massively important and makes using it for a first stage is really, really difficult. Second stage is somewhat difficult, but once you've got into orbit, there are no effective gravity losses and there is no problem with the thrust. Now, what about the upsides? First of all, it's got a much, much higher ISP. Secondly, it has an easier route to sustainability of green hydrogen compared with biomethane. And finally, you could argue it's actually easier than methane for in-fuel or in-situ fuel production. I'm just going to outline some assumptions before people ask questions. I'm assuming there's already a fuel depot in orbit. The HLS is based on the V1 size for Methalox, and around about a 35% tank length increase for Hydrolox. There must be dedicated refueling ships. I'll talk about the payloads later. And we're going to use the Vacuum Raptor 3 and an increased Bell size RS-25. And I'm going to suggest that there's a removal of all the additional engines that were needed to launch it, stripping it down to 2 or 3 engines. That's all you really need for getting to the moon, landing, etc. Now, what about Delta V? Well, before we move on to that, if you enjoy that, please hit the like button, or if you enjoy similar content, the subscribe button. The Delta V budget looks like this, using idealized Hohmann transfers. That's from low Earth orbit to lunar insertion. That's a low lunar orbit, which I expect it to be, not on the distant retrograde orbit at the moment. Gateway will be much later. Deorbit and landing, takeoff and rendezvous. That's 6,900 meters per second. Never would this actually happen. So using Apollo numbers, they bumped up TLI. They got there a little bit quicker. 3,200 meters per second, added 100 there. Their landings were significantly more, about 2.4 and 2.2. I've taken the middle numbers. Why? You need margin. You also need possible, if you're going to need an abort before landing, you may have to have inclination changes, orientation changes, depending on where you're landing. So therefore, I'm going to take a 8,100 meter per second Delta V. This is an estimate, so it could go up, it could go down, but the actual split between Hydrolox and Methalox will stay very similar. So for engine efficiency, I'm going to use the Raptor 3, optimized for vacuum, and there seems to be a suggestion it's around about 380 seconds. For Hydrolox, we're going to take the RS-25 and we're going to slightly expand the nozzle to increase the ISP, matching what the RL-10 would have, which is 466 seconds. Now, I cannot make this point any clearer. Aluminium is key. We need to reduce mass to reduce fuel load. And look at the relative densities. 7,500 kilograms per cubic meter for stainless steel and 2,800 for aluminium. Now, you can't use the whole ship. It's not all going to be changed into aluminium, but there are massive savings here. The all-important dry mass and payload. I am going to consider that if we start with 120 tons for a stainless steel ship, we can use aluminium. Why? There's no heat shield, there's no flaps, there are no thermal issues re-entering into the Earth. Now, I'm suggesting about 50% of it can go from stainless to aluminium. Not all things can. You have landing systems, you have other systems. That would bring us down to about 80 tons for a methalox. That's for a V1 booster. Now, there's good reason for suggesting this number. Why? If you look at the SLS core stage, it has a volume 20% larger, and it's an aluminium, than the V1 ship. If you downgrade that, and that's 88 tons dry mass, and recognize there's actually one less engine on the V1, you could easily get to 80 tons or below. I brought it up at 80 tons because there are some other systems. Now, for the hydrolox, it needs to be a little bit longer, about 8 or 10 meters longer. That's only going to be in the aluminium tube section. My suggestions are 12 to 15 tons. I've added a little bit more because perhaps it might need a little bit more for cryocoolers or additional cryocoolers, and for perhaps the RS-20s being heavier or a greater mass. That's 100 tons for the hydrolox. Payload, I'll talk about it in a minute. Payload is what I mean is fitting out the astronaut area, 20 tons. And finally, residuals, 2.5% of the fuel mass. So what would the payload include? Certainly you're going to need life support, you're going to need supplies, you're going to need an astronaut space for somewhere for them to live in, and there might be rovers, lunar equipment as well. To get your fuel budget, which is literally based on the amount of delta V required, we take the ideal rocket equation, which a simplified version is there on the top. We reorder it to find the total initial mass, MO, where MF is the total final mass, and then we can find out the fuel required. So how many refillings? Methane, according to the equations, comes just under 1,000 tons, and hydrogen just under 700 tons. But for some reserve, we'll put it at 1,700. What does this mean? Under ideal refueling techniques, that requires 5 orbital refillings. Hydrogen, 3.5, considering the fourth one will only be half used for refilling with hydrolox, and half of it can be for another payload. So just making that a little bit clearer, let's imagine you had a version 2 Starship that only had 100 tons mass to orbit, then you would need 10 refillings for the methane, 7 for the hydrolox. But if you can actually have the 200 tons, it brings it to 5 and 3.5. So to sum up, hydrogen or methane? Yes, methane is easier to handle, but not that simple. Hydrogen is more complex, but there is evidence, reasonable evidence, that it could still work. And here's the point. If we use aluminium, then therefore there is a 30% reduction, roughly, in the amount of fuel that's needed. This reduces the amount of dedicated refillings. Now, of course, all of these scenarios are based on ISPs, masses, and impulse burns. But what do you think? Does hydrogen make sense? Or should we stick with methane? Drop in a comment and perhaps add your explanation.